Spoke-to-spoke Flex VPNs. Let's begin. Earlier in this course, in our videos about dynamic multi-point VPN, we learned about NHRP, the Next Hop Resolution Protocol, and that we could use it for spokes, for example, to discover and be able to build direct paths between each other. So they didn't have to forward all the traffic through the hub every time we wanted to have spoke-to-spoke communications. Well, guess what? That NHRP stuff is so slick and so cool that we also use it as part of FlexVPN for the same exact purpose. In fact, the only thing we need to do to make this work in a FlexVPN with Ike v2 is we're going to add these two commands to the hub. And on the hub, we have a dynamic virtual tunnel interface. So these commands would be applied to the virtual template on the hub. So if R2 sends a packet that's destined for 10.4.4.4, and R1 receives that packet on an NHRP network interface, for example, an interface that's part of network 1, if the next hop is also on network 1, R1 can go ahead and send a redirect back to R2 saying, you know what, buddy, there's a better path. And R2 will say, well, that's great. I need the details about that better path. Can you please give me the information regarding how to reach that next hop? Now, in this case, if it's R4 who owns that next hop address, R2 sends the NHRP request to the hub forwards it to that spoke who owns that address, and then the spoke can reply directly back to R2 and say, hey, here's the answer to your question. Here's the reachability information. And at that point, these two devices can negotiate and build an Ike v2 and the child SAs for direct spoke-to-spoke communications using NHRP as the mechanism to enable that. Now on the spokes, we're going to go ahead and create a static tunnel interface. For example, tunnel 0. And that tunnel interface says, okay, the hub is the destination based on 15001, and the source is Ethernet 00. And that static tunnel needs to be there to get the ball rolling so that R2 will check in, if you will, and start the tunnel to R1 for that hub and spoke connectivity. However, if we're implementing NHRP as well, and R2 decides it needs to build a direct path between R2 and R4, this tunnel interface, we've got a problem with it. It is not a multi-point GRE interface like we used in dynamic multi-point VPN. So to accommodate that in FlexVPN, what we're going to do is we are also, on each of the spokes, going to create a virtual template interface that can be used to create the virtual access interfaces. So if R2 and R4 need to talk directly with each other, they can generate and spawn off a virtual access interface just for that dedicated point-to-point connection between R2 and R4, which is going to be protected by IPsec. So although the static tunnel and the dynamic virtual tunnel interface are nothing new, we've seen them both, we haven't seen them both configured on the same device. So look for that on each of the spokes. The other thing that we're going to do on each of the spokes is we're going to use the IP NHRP network ID. That network ID of 1 in this example needs to match the hub's network ID. And we're also going to put the IP NHRP redirect command also on the spokes. Now, normally that would just go on the hub. However, adding the IP NHRP redirect to the spokes gives the spokes the opportunity to send redirect messages to each other in the event that they know of a better path to get to a given destination. So if we look fairly closely, these two commands and these two commands are identical. So these two NHRP statements on the hub and the spoke, those two are identical to each other. And on the spokes, we're going to apply those to the static tunnel and to the virtual template interfaces. This third NHRP command is specific just for the spokes. It's IP NHRP shortcut, and that tells the spokes to go ahead and initiate a direct connection to another peer spoke as long as they have the NHRP resolution done and know the reachable addresses for that peer. Now, if these spokes choose to do this, they also need to know which virtual template to use to create this new virtual access interface for that spoke-to-spoke connection. And that's why the IP NHRP shortcut command, which is at that point very similar to what we had in DMVPN. However, now we are linking with this command, this virtual template, to tell them which one to use, and we're adding that to the IP NHRP shortcut command. Now, in creating the demonstration for this, I realized that we've been doing a lot with FlexVPN, and so to give us kind of a nice fresh slate, I have reconfigured all of these routers to have no specific cryptography configuration whatsoever, with the exception of they do have digital certificates, meaning that they've created a public-private key pair, they've authenticated with a common CA that they all trust, and they've also enrolled with that certificate authority, so they each have their identity certificates. That means that if we want to use RSA signatures, the digital certificates are sitting there waiting for us. However, everything else regarding Ike v2 is in their default state on routers 1, 2, 3, and 4. So to start off, let's go ahead and go into configuration mode. We'll type in AAA new dash model, and instead of creating a specific network authorization method list, let's go ahead and specify the default network authorization method list, and then we can call on that list. Next, we're going to modify the IKE v2 authorization policy called default. We'll use a pool called FlexPool to hand out IP addresses. We'll do a route set for interface and route set for access list hub-ACL. And what that means is we're going to push down to our spokes the IP address of our interface, as well as the networks that are identified in the access control list called hub-ACL. Now, because this is a fresh config, there is no access control list called hub-ACL, so let's create one. We'll type in IP, access-list, standard, the name of the ACL, and then we'll say permit 10.0.0.0 with a wildcard mask of the last 24 bits not mattering, and as a result, this 10 network will be advertised as reachable from the hub down to the spokes. In our authorization policy, we also called upon the pool called FlexPool, which isn't yet defined. So to define an IP local pool, the syntax is IP, local pool, the name of our pool, then the starting IP address, and then the ending IP address. Now regarding our IKE v2 proposal, we have several options. We could use the default, we could tweak the default, or make a new one. In this case, let's go ahead and just modify the default to use encryption 256 AES, data integrity SHA-256, and Diffie-Hellman group 14. Next, let's go ahead and create the IKE v2 profile called default. And for identity, let's use the local FQDN of r1.cbtnuggets.com. Now this is a little bit different than we did in our previous videos. Previously, we were basing our local identity on the distinguished name, which was pulled from the cert. So we're enjoying a little bit of variety with this config. Another trick that we can use for scalability is we could do our match statement. For example, match identity remote based on the fully qualified domain name, but we could say the keyword domain and just identify cbtnuggets.com. So even if we're using pre-shared keys, as long as all of our branch offices have the domain configured locally for their identity as cbtnuggets.com as part of their ID, that one match statement will match all of them. Now you might be saying, well, we don't want just anybody to connect if they're cbtnuggets.com. And of course, that's why we have the authentication on top of our IKE v2. And in this case, we're still going to use RSA signatures for the local as well as the remote authentication of the peers. If we want the ability to validate and use digital certificates, we need to identify our local trust point that we've defined on this router, which is trusted-CA. And we also want to specify how we're doing the AAA authorization with AAA authorization group based on digital certs, meaning if we've already authenticated that peer via digital certificates and RSA signatures, that's 2 thumbs way up regarding authorization as well, because the method list called default says use the local router. And the last word default is referring to our default authorization policy. And because on the hub we're going to be using a dynamic virtual tunnel interface, we need to include or specify what the template is to go ahead and create the virtual access interface that's going to be used for a connection to a peer. Now when we create the virtual template, I want to use IP numbered and point back to a loopback interface. Just to make sure we're nice and clean, I'm going to create a brand new loopback interface called loopback 10 and give it the IP address 172.16.1.1. And now when we create our interface virtual-template1 type tunnel, we'll simply use IP unnumbered and link it back to loopback 10 that we just created. So the IP address for the virtual template and subsequently the virtual access interfaces that will be created is going to be 172.16.1.1. Now my friend, here's the trick for doing the spoke-to-spoke direct connections. You know how in dynamic multi-point VPNs we had the IP NHRP configured, the next hop resolution protocol? Well, guess what? We're going to use that same technique here on the hubs and spokes with IP NHRP network ID, give it a number, and IP NHRP redirect. So the network ID for NHRP needs to match between the spokes and the hub. So we're going to give the spokes the network ID of 1 as well. And the NHRP redirect here on the hub is instructions for the hub if it receives a packet with the next hop where R1 knows, hey, there's a better, more direct path. It can send a redirect message back to that spoke, which will help encourage that spoke to go directly to the source. For example, R2, instead of going to the hub to get to R3, R2 would be encouraged to go directly to R3. Now the next challenge for R2 is how does R2 find out about the addresses to reach R3 directly? And to solve that, R2 is going to do an NHRP request up to the hub. When the hub gets that request, it's going to forward it to the correct spoke, in this case R3, who can then reply back to R2. R2 has the information it needs, and now R2, armed with the information it needs, can do an IKE v2 negotiation directly with R3 to build the tunnel. Our last step on this virtual template interface is to go ahead and apply the IPsec profile with the syntax tunnel protection, IPsec profile, and we are going to use the default IPsec profile. However, there is one little thing we need to add, and that is this. We need to go into that IPsec profile call default and tell it that we want to go ahead and use the IKE v2 profile. And that just guarantees that they are linked together. Now, what I wanted to point out with you with this template that we just created is that something is different compared to all of the other templates that we've created. And that is, I didn't assign tunnel mode, IPsec, IPv4. It is not in this configuration. And if we don't specify the tunnel mode, the default tunnel encapsulation is GRE, Generic Router Encapsulation, which is protocol number 47. However, because we have the IPsec profile, the GRE traffic is still going to be encrypted and encapsulated in IPsec and be sent. So by using tunnel mode, IPsec, IPv4, we're cutting off a little bit of overhead that the GRE would add. But I wanted to point out in this video that you can do it either way. It's not required that you say tunnel mode, IPsec, IPv4. But if you do, it's going to save us a little bit of overhead. Next, let's make a road trip over to R2, and that's our first spoke that we're going to configure. And we'll go into configuration mode on R2. And on R2, let's set up the default authorization policy so we can push specific routes up to the hub. So we'll say route set interface for the interface IP address, as well as route set access list R2-route-ACL, which we would need to create. So if R2, for example, has a network of 10.2.2/24, we can include that in the access list, and that information, that routing information, will be advertised up to the hub. So we'll create that access list while we're thinking about it. IP access-list standard R2-route-ACL, and we'll say we want to match or permit the 10.2.2/24 network. Next on this spoke, we're going to make a compatible default IKE v2 proposal. It needs to match at least one of the integrity and hashing and Diffie-Hellman groups that are over on R1. So to do that, we're going to simply mirror it. Encryption is going to be AES 256, integrity SHA 256, group 14, exactly what R1 has. Next, we'll go ahead and create the crypto IKE v2 profile default. We're going to match identity remote based on fully qualified domain name, as long as the domain portion of that fully qualified domain name is cbtnuggets.com. It's a match. And our local identity, the fully qualified domain name of r2.cbtnuggets.com. We're going to use RSA signatures for our authentication on the local side and the remote side. And we'll also specify our trust point that we've locally defined here on R2, which happens to be also called trusted-CA. On R2, because we do want to be able to use our authorization policy and be able to advertise this network of 10.2.2, which is in this R2 route ACL, which is in our default authorization policy, we're going to use the command AAA authorization group cert, implying that if we've authenticated the peer, they're authorized from our local perspective, and then list default and then the authorization policy called default. Now, on this router, I did not explicitly create a network authorization policy called default. So if the router's default attitude is the local router itself, we're in good shape. If it fails, that's the first thing I'm going to come back to take a look at. But I think we'll be okay even though we didn't explicitly define the default network authorization method. And should the need arise for this spoke to ever dynamically create a virtual access interface, we're going to point to the virtual template from which you can go ahead and clone that information to create that virtual access interface. Now here's a spoiler alert. If we have R1 and R2, and over down here we have R4, and R2 is trying to reach the 10.4.4.4 network, and R2 sends a packet to the 10.4.4 network, and R1 sends an NHRP redirect message, which causes R2 to send an NHRP request, which when R1 gets it, it sends it to the spoke who owns that address. And then R4 can reply directly back to R2 saying, hey, here's my IP address, here's what you're looking for. At which point R2 can say, great, I want to go ahead and do an IKE v2 negotiation with you. And using this virtual template, it can create a virtual access interface for that new dynamic connection spoke to spoke between R2 and R4. So that direct shortcut from spoke to spoke is where that virtual template on the spoke is going to come in very, very handy. We are going to use the default IPsec profile, and I want to include in it our IKE v2 profile call default that we just defined. Now here's a very interesting part in getting the ball rolling. On R1, we can use the dynamic virtual tunnel interface using the template for all the connections, because R2 will initiate the connection, R4 will initiate the connection. But in order for R2 and R4 to initiate connections to the hub to get the ball rolling, they have to know what that IP address is of the hub, and it has to be configured somewhere. So here's what we're going to do. On R2, we'll have a tunnel interface, let's call it tunnel 0, that has the destination IP address of the hub. So it's got the tunnel source, the tunnel destination, and the same thing for R4. The tunnel 0, for example, will have the tunnel source, the tunnel destination, pointing to R1. And that's how we get the ball rolling. However, when R2 decides it needs to go ahead and directly communicate with R4 because of the NHRP redirect and the NHRP resolution, when R2 goes to R4, that's when it'll use the virtual tunnel interface, specifically the dynamic virtual tunnel interface. Using the virtual template, it'll clone out and create the virtual access interface to go ahead and communicate directly between R2 and R4. So to pull this off, the spokes are going to have a static tunnel interface that basically phones home to the hub. And they're also going to have dynamic tunnel interfaces using virtual templates so they can dynamically create sessions on the fly to each other when needed. So let's create the tunnel interface. Let's use tunnel interface 0, and we'll do IP address negotiated so we can pull an IP address from the pool that's being offered by the hub. We're going to specify the IP NHRP network ID of 1. Now why 1? Because that's the number that we used up at the hub. It has to match. The next challenge is if R2 learns that, hey, there is a better path to get directly to this other spoke, like R3 or R4, which interface should I use to go ahead and connect to it? Now with dynamic multi-point VPN, we had a multi-point GRE interface. And the multi-point GRE interface could have lots of different terminations on it. However, with dynamic virtual tunnel interfaces, we're spawning off and creating separate virtual access interfaces for each connection. So here on R2, we'll say IP NHRP shortcut, if you need to do it, please use virtual template number 1, and we'll need to define the details for virtual template 1. Now this command is typically in DMVPN only done on the hub, the IP NHRP redirect. However, if we have several spokes that are communicating with each other and one spoke knows about a better path to yet another spoke, why not also have that redirect capability on a spoke so it can give its buddy, another peer, information about a better path to get to yet another spoke. So for that reason, I'm including the IP NHRP redirect also here on R2, the spoke. And then finally, we're going to specify the source address for this tunnel interface, the destination, which is our headquarters 15001, that's R1's address, and we'll also protect that tunnel traffic by using tunnel protection IPsec profile default, which is the name of the default IPsec profile that we're using. Now you'll also notice here that on this tunnel interface, I did not include tunnel mode IPsec IPv4. We could have, and if we do, we'd want to make sure we apply it everywhere. So either put it everywhere or don't put it everywhere. And on the hub, there's also, depending on your version of iOS that you're running, there's an auto mode where it can automatically detect the inbound connection and automatically use the appropriate mode. Not all versions of iOS have that feature. So I would have you err on the side of caution. Either use it consistently in your environment or don't use it at all. So in our demo in this video, I am not including anywhere the tunnel mode IPsec IPv4 just to make sure it's consistent on the hub and all the spokes. Next, let's create our virtual template interface. We'll use template number 1, type tunnel, and we'll say IP unnumbered tunnel 0. Now this is a little bit sneaky. And the reason it's a little bit sneaky to use IP unnumbered and point to the tunnel interface is because this tunnel interface is using IP address negotiated. So whatever IP address the hub gives this spoke on the tunnel 0 interface, that same IP address will also be used on the virtual access interfaces that are created based on this template. Now on this virtual template interface, we're also going to specify NHRP commands of IP NHRP network ID of 1, the IP NHRP shortcut pointing back to this virtual template in the event we need to create additional virtual access interfaces, and IP NHRP redirect for the benefit of helping out a brother or a sister, another spoke who has sent a packet and we know a better path on the same NHRP network, we can go ahead and do a redirect. And then we're going to cloak this virtual template interface in security with tunnel protection, IPsec profile, and the name of our IPsec profile. In this case, we're using the profile called default. And that is it. Now the syntax for router 3 and router 4 is virtually identical. Now what we are going to change, for example, are the access list contents for the authorization policy. For example, R3 doesn't have the 10.22 network, so we're going to change that. And then the profile on R3, his local identity wouldn't be r2.cbtnuggets.com, it'd be r3.cbtnuggets.com. And what I think would be fun is let's go ahead and configure R3. We'll do it a little bit faster, but we can use that to help reinforce the concepts of implementing FlexVPN with the spoke-to-spoke connectivity. So we'll make our road trip over to spoke R3, and on R3, we'll modify the default IKE v2 authorization policy, the one called default. We'll do route set interface, which is actually on by default. We'll also do a route set access list R3-route-ACL. So we'll be advertising the interface address that we have as well as the contents of that access list as reachable, and we'll advertise that up to the hub. Next, we'll create that access list called R3-route-ACL, and inside we'll match on the 10.3.3 subnet with a wildcard mask of 8 bits at the end. So we care about the first 24 bits, we don't care about the last 8. We want to make sure that our IKE v2 proposal matches, and we're using the default on R1 and R2, so we're going to modify the default here as well. We'll specify that for confidentiality, we're going to use AES-256. For data integrity, for hashing, we'll use SHA-256. Diffie-Hellman group 14 is perfect because that's the only Diffie-Hellman group we have configured on R1 and R2. And if we ever want to be able to build tunnels with them, we'll need a compatible IKE v2 policy. Next, we'll create our IKE v2 profile. We're going to call this default as well. We're going to match based on identity remote using the fully qualified domain. If the domain portion is cbtnuggets.com, it's a match. Our local identity is the fully qualified domain of r3.cbtnuggets.com. We're using RSA signatures, courtesy of digital certificates for the authentication locally and remote. Our trust point for our certificates is called trusted-ca. And our group authorization is going to be based on the default authorization policy for IKE v2. And then we'll link this to the virtual template number 1, which we will still have to create. And again, that virtual template will be used to create the virtual access interfaces for the spoke-to-spoke communications. Next, we're going to tuck into our IPsec profile called default the IKE v2 profile called default, so they're linked together. Next, we'll create our tunnel interface. This is for the initial connection to get the ball rolling between, in this case, R3 and R1. We'll do IP address negotiated. The IP NHRP network ID of one has to match the others. The IP NHRP shortcut says which virtual template to use if you're going to do a direct path. And IP NHRP redirect for the benefit of helping other devices out if you know of a better path on the same NHRP network. We're also going to specify that the tunnel source is E00. The tunnel destination is the IP address of R1 at 15.0.0.1. And we're going to protect this tunnel with the IPsec profile called default. Again, notice no tunnel mode IPsec IPv4. It's not being used on the hub. It's not being used on the spokes. It's just being consistent in the topology. Last but not least, we need to go ahead and create the virtual template interface. We'll use virtual template 1, type tunnel. We'll use IP and numbered pointing back to the tunnel 0 interface, IP NHRP for the network ID, for the shortcut, and for the redirect. So on the hub, we really don't need a shortcut command. There's no new direct paths that it should have to go ahead and learn. Hopefully the hub, in a hub and spoke topology, has the most direct path already to all of the spokes. Now we have one last spoke to do, and we're going to take this one even a little bit faster because it is, again, virtually identical to spoke router 2 and spoke router 3. So on R4, we'll get into configuration mode. We'll go ahead and modify the default IKE v2 authorization policy. We'll include, for the route set, an access list called R4-route-ACL. Now inside that access control list is going to identify the local networks that R4 has. And that way we can notify, over the IKE v2 tunnel, we can notify the hub of what those networks are. So once we have identified that list inside of the default authorization policy, we'll create that access control list. Next, we're going to modify the default IKE v2 proposal to match the integrity, encryption, and Diffie-Hellman group that's currently being used not just on R1, but also on R2 and R3, because that's important if we're going to build those spoke-to-spoke tunnels. Next, we're going to go ahead and create our IKE v2 profile called default. We specify the match identity remote, the local identity, the authentication method that we're going to use. In this case, it's RSA signatures because we have our digital certs already in place. We'll also specify the PKA trust point that we're going to use to authenticate and use those digital certificates. We're also going to use AAA authorization group, cert list default. Again, referring back primarily to the IKE v2 authorization policy called default. We're also going to tuck the IKE v2 profile called default into the IPsec profile called default just to err on the side of caution. We'll create our tunnel interface tunnel 0. We'll use IP address negotiated. We'll put the IP NHRP details in, the network ID, the fact that we want to do a shortcut, and if we do, what virtual template to use, and the IP NHRP redirect. We're also going to specify the tunnel source is our local interface facing the internet, and the destination is 15001, which is the reachable IP address of R1, the hub, and we put our IPsec profile on top of that tunnel interface. Last but not least, we'll create our virtual template interface. Virtual template number 1, type tunnel, IP unnumbered, pointing back to that tunnel 0 interface, IP NHRP statements for the network ID, for the shortcut and which virtual template to go ahead and use, and also for the redirect. We'll also apply our IPsec profile to this tunnel with the syntax tunnel protection IPsec profile and the name default, which refers to the default IPsec profile. So let's do some basic connectivity testing and verification of our tunnels. We'll do a ping to 10.1.1.1. That should be reachable. That is the network sitting behind R1. We have reachability there. That's great. If we do the command show crypto session, that's a nice tidy way to see our IKE v2 and our child essays. And this indicates that tunnel 0 is up, status is active. Our peer is 15001. We negotiated that on UDP port 500, which is the default for the IKE v2 negotiations. The two ends of the tunnel are 45004, which is us, and 15001, which is R1. And for IPsec, we have two security associations, one that goes from us to R1 and one that goes from R1 over to us. And it says origin crypto map, and that's just a little bit of legacy creeping in. We didn't actually use a crypto map. We literally used an IPsec profile applied to our tunnel interface, tunnel 0. Now we also should be able to ping 10.2.2.2. That's the subnet hiding behind R2. Let's try that with a ping of 10.2.2.2. You'll notice something amazing happened. Now we lost the first little ping. The first ping response didn't come back, and that could be due to either ARP or, in our case, very likely due to the IKE v2 and child SA tunnels all being negotiated and coming up. Because you'll notice what happened. We now have this interface virtual access 1 change state to up. What that implies is that the virtual template was used. It created a new virtual access interface for the logical connection directly between R4 and R2. So now if we do that same command that we did before of show crypto session and take a look, now we have two current sessions in place. We have the one on tunnel 0, which was there before, and we have this new one that's using virtual access 1. And for the IKE v2 tunnel, the local site is 45004, that's us. And the remote site is 25002, that is R2. And we've got two child essays, that's the IPsec essays, where the actual transit traffic, our ping traffic for example, can go back and forth. But wait, there's more. What about R3? Let's go ahead and do a ping of R3 at 10.3.3.3. Now, in the background, what's happening is there's a redirect message coming from the hub. There's an NHRP request that goes out. That request goes up to the hub. R1 sends it over to R3 because that's the destination that owns that address. And R3 responds back to R4 with that next hop information that R4 needs to go ahead and build the direct tunnel to R3. And you'll notice we now have virtual access 2 that has just popped up. So now if we do the command show crypto session, we're looking for 3 IKE v2 tunnels and their associated children essays. So virtual access interface number 2, which was cloned and created from the virtual template just for the purpose of the IPsec conversation between R3 and R4, has a single IKE v2 tunnel and 2 security associations as children tunnels. And those again are the IPsec security associations, one for encrypting traffic from R3 to R4 and the other for encrypting traffic from R4 over to R3. If we want to take a look at just the IKE v2 essays, of course the command hasn't changed. It's show crypto IKE v2 essay. And the details regarding confidentiality, the hashing, the Diffie-Hellman group, and the authentication method are all shown here for each of those tunnels. Other familiar commands like show crypto engine connections active can also be used. Again, for that kind of bird's eye view of all of our sessions that are in place. So we have 3 IKE v2 sessions. R4 to R1, R4 to R2, R4 to R3, and each of those IKE v2 sessions have 2 children essays. And we have encrypted and decrypted traffic on each of those essays, which is a very good sign. Now in this course, the concept of NHRP was first introduced back with DMVPN, Dynamic Multipoint VPNs, and those NHRP commands, most of them can still be used right here because we're still using NHRP. For example, show IP NHRP enter or show IP NHRP shortcut would provide information about what's in the cache that R4 is using to reach those other spokes. So here R4 is saying, okay, to get to the 10.2.2 subnet via the next hop 1.2.16.0.100, I know that the reachable address is this guy, 25002, which is the public-facing IP address on R2. And similar treatment of 10.3.3. The next hop for that was 172.16.0.101. And this address, which is the tunnel address, is reachable by the outside address of 35.003. And you know what one of the coolest things is? We didn't have to configure any dynamic routing protocols in this hub and spoke topology because the hub is advertising the 10 network as a /8, and all of our spokes are using 10 something. That allows all of our spokes to have a route to the 10, and when they start to try to use it, then they get the redirect message, and then based on that redirect message, them doing an NHRP request to learn this information, they can go ahead and start using this to talk directly with that spoke. And NHO right here refers to next hop override. If we want to see that in the routing table, if we do a show IP route, there's more to the routing table, but I want to focus just on these two routes right here. The percentage sign means it's a next hop override route. Effectively, it gets high priority in the routing table. So if we were learning these same routes of 10.2.2 and 10.3.3 through a dynamic routing protocol, such as OSPF or BGP or RIP or EIGRP, due to the NHRP and the next hop override, these are going to be placed in the routing tables as best routes. And why are they the best? It's because they are literally the quickest path between 2 points is a straight line. So between R4 and R2 and between R4 and R3, these virtual access interfaces are indeed the most direct path, the straightest line between those two devices for reaching R2 and R3 respectively. Now another test, just to verify full connectivity, is we could ping 10.2.2 and source it from our 10.4.4, and that would also confirm that R2 has reachability back to our subnets that are hiding behind us. And to confirm that we're not going through the hub as well, we could do a trace route to 10.2.2.2. We could source it from our local 10.4.4.4 just to verify that it's a direct shot between us and R2. And it is. We have one single hop of 172.16.0.100. And if we scroll up a little bit and take a look at our NHRP output, 172.16.0.100 resolves to 25.0.0.2, which is the public-facing IP address of R2. To assist you in your practice, I've included in the Nugget Lab files associated with this course this document called Spoke to Spoke FlexVPN with full configs. And what it has all the configuration that we implemented on R1, R2, R3, and R4. And at the end of it, it has the full running config displayed for R1, 2, 3, and 4 as well. So as you implement this and practice with it, if you're going to use pre-shared keys instead of digital signatures, you want to create the key ring and modify the IKE v2 profile to reflect that. And again, I provide this as a reference point of a working configuration that matches what we did together in this video. I've had a great time. I'm glad you joined me for this video. I hope this has been informative for you, and I'd like to thank you for viewing.